So compute the volume of the solid bounded or formed by the intersection of the surfaces. Z equals x squared plus y squared minus 3, and then 3 minus x squared minus y squared. All right, so very similar to the problem that preceded it, right? But it's one of those things. If you didn't understand what the heck I was talking about for the previous one, then this is your second crack at it. But it's also challenging in its own right. Right? So I think a good way to get started on this, and really, I think this is going to consistently be the case, is to start thinking about what system, whether it's rectangular or polar, or when we get to it spherical, is the most appropriate for these equations. All right, and so when you look at the graphs themselves, they're cone shaped. They're parabolic. Can't even talk parabolic in nature, but they do have a conical aspect to them. Right, just a curved edge or a curved vertex. So that does seem to imply circular. Right? If it's a circular function, you might be tempted to go with a polar or cylindrical coordinate system. Right? So that's a good place to start. Right? Personally, whenever I see an x squared plus y squared, I'm just going after polar immediately, because x squared plus y squared is equal to r squared. Right? We know that relationship. So I can make that substitution right off the bat, right from the get-go, as they say. What did get-go have to do? All right. Now for the other one, all right, let's factor out the negative first. In which case we're going to get a 3 minus r squared as the value of z, or as the equivalent to z. All right, so I have two equations, two variables. I could find the intersection of these two in terms of r, because if they're both equal to z, we can set them equal to each other and say that r squared minus 3 is equal to 3 minus r squared, which would give us 2r squared, if I add r squared to both sides, is equal to 6, making r squared equal to 3, making r equal to, normally we would say plus or minus the square root of 3, but since this is going to be a circular function, we don't have to worry about the negative, because it's just going to trace out the path of a circle in a different direction. Right? I just care about the path of the circle, not the movement along that path. Right? So I'm just going to go with a radical 3 here. All right. So what that gives us, again, is the intersection. That intersection appears to be in this neighborhood. All right. It's not going to be perfect in terms of the diagram that I draw, because that's just me. Sorry, I got a little kink in the jaw there. But I mean, I suppose that could be a radius of the square root of 3. Square root of 3 about 1.7. Okay, maybe not. I mean, it seems to be right in the neighborhood of that 3, but I'm not betting my life on the quality of my diagrams regardless. So more confident in the math than the ability to draw a picture. All right. So that seems to be the outer extent. Now, what I can do is find the volume that's contained between the downward facing paraboloid and the upward facing paraboloid one of two ways. One way, because there is symmetry, right? We're looking at one that is a reflection of the other through the XY plane, right? And that's because if you just look at r squared minus 3 and compare it to 3 minus r squared, they're exact negations of one another. All right. So if you negate z, you're making a reflection through the XY plane. It's kind of like if you negate y, you're making a reflection over the x-axis in two-dimensional rectangular coordinates. Here, if you negate z, you're making a reflection through the XY plane. Right. So if we find the volume contained between the upper function, right, z equals the one that's facing downward, right? That would be z equals 3 minus r squared. we find the volume contained between that and the XY plane between 0 and radical 3, we would just have to double that, right? The other way of handling it would be to find the volume contained from the upper function down and subtract from that the volume contained from the bottom function. Yeah, so that one is a little bit kookier. Right? So it's really just finding the difference between the two functions and then creating a volume double integral out of that. But go with the simpler way, obviously, I think. So, oops, kind of jumped on me. So what I'm saying here is let's figure out this guy. And this is the volume. Oh, that's not going to be good. I don't even know why I bother. All right, pretend that looks awesome. All right, we're going to find the volume contained beneath that paraboloid in the XY plane and then double it, right, due to symmetry. Symmetry is a beautiful thing. Right? So the z function that I'm concerned with here would be the 3 minus r squared, r dr d theta. Now that's happening if we bring it down to the xy plane, right? You think about the graph in the xy plane, it is the r equals the square root of 3. All right, it just kind of works out that way, which is nice. It's not always something you can bank on, right? Because if it's offset in any way, like the previous problem, and I think, let me just double check, the next problem is offset also, I believe, where the intersection is not in the xy plane. What you'd have to do is figure out what the bounds would be in the most extreme sense, which may or may not be in the xy plane. In this case, since it is, and it happens also to be radical 3, we're in good shape, right? But if you wanted to take a quick look at it in the xy plane, that purple circle is going to have a radius of radical 3. Oh, geez Louise. Believe it or not, there are people out there who can actually draw. Shocking. Right, so this is the radical 3 radius. Now, what we're getting here is the top-down view of the paraboloids intersections. Right, so what we can do is if we really want to get a true sense of this, or at least get a good feel for it, z equals x squared plus y squared minus 3 right into GeoGebra. Z equals 3 minus x squared minus y squared. So do it in rectangular coordinates. Okay, so again, that little pill-shaped region is the area that we're concerned with. If you do a top-down, you kind of get a sense of it. Let's do this little finagling here. But I could also graph the circle center at the origin, or 000 basically, with a radius of radical 3. But I could do that in a couple of ways. One, I could do it as a parametric graph, which seems to be more trouble than it's worth. Another way to do it would actually be to graph the cylinder that would intersect with the XY plane, having an intersection that traces out the circle r equals the square root of 3. So that's what I'm going to do. I'm going to type in x squared plus y squared equals 3. And let me change the color on that so it pops a little. Oh, I'm trying to do it like I'm trying to do it like Desmos, where you just long press on it. All right. So let me do a better zoom job here. Home, I guess home. Let me bring it out. I don't even know what just happened. So what else is it? Yeah, so you can see hopefully that cylinder is intersecting, and I'll try to get this in a different color here also. That just made it worse. Something light and airy, right? So the orange and the red are intersecting to form a circle. That cylinder is intersecting that circle also, right? If you do a top-down view, you can see that that seems to be the boundaries or the boundary of the top part of that pill-shaped figure, all right, bounded by that cylinder. If you go to just the XY plane, it seems that the outer bounds would be the circle x squared plus y squared equals 3, or r equals the square root of 3. Right, so it's a good visual option, to get a good sense of what's going on. All right, so we know that if I want to capture all of that figure, all right, that top part of that pill, I have to go from the center 0, 0, 0 in rectangular, or just r equals 0 in polar, to radical 3, outward to a radical 3, right? So what I'm doing here is I'm just kind of working my way out from center until I fill up all that space. Started looking pretty bad. All right, but I got to do that all the way around. So I wouldn't just limit myself to that first quadrant. I'm working my way all the way around, getting myself eventually to 2 pi radians. Yeah, it got a little out of whack now. Oh, look how gorgeous that is. Yeah, 0 to 2 pi. So shooting all the way around. I'm trying to make these look like arrowheads. It's not working very well. All right, but going all the way around, that complete turn around the XY plane tells us that this ought to be 0 to 2 pi. All right. Now, this one's easy enough to actually compute. Just, you can't forget that that's only giving you the top half. If I want the bottom half, I'm going to double it. All right, poor quality writing because it's too light. All right, so we're going to double that to give us the bottom half also. All right, so we could actually do this one by hand. If you remember from last class, I said that I was taking it as bonus, and I awarded this bonus already to change the directions just so that you're writing an integral or sum of integrals that can be used to find the volume contained blah blah blah. All right, so this is actually where I would tell you to stop. But like I said, this one's actually not too bad because it's the product of this and this that's just going to end up being a cubic function, and that's pretty easy to work with. All right, you're integrating with respect to r, it's going to give you a constant value. Then you're integrating with respect to theta, which is going to give you another constant value once you plug in a 0 to 2 pi, and then you'll get the result. All can be done on the calculator. All right, so we don't need to go any further than that, and I'm not going to ask you on the test to go any further. Sorry, just taking off the back brace. So, and I think most people agree that the challenge really isn't the active integrating, especially for a problem like this. It's more so coming up with the double integral that gets the job done. Right. So the volume of the solid formed by the intersection of the surfaces. So here we got a cone. We definitely have a cone, a triangular cone, instead of a circular, instead of a parabolic cone. And you have something that looks also like a parabola, all right? In terms of the overall strategy, not going to be too different than what we just did, except I don't see any coordinate axes here. So we're going to have to do a little bit of work to figure that part out. All right. So now, that being said, just because I put a graph in here, oh, dang it, see a little stray mark there? Take it as a typo. It's hard to tell, but now I'm starting to get nitpicky. See this? I'm just whiting it out now. Little stray mark on the bottom of page 75. That shouldn't be there. So I'll take that as a typo. All you got to say is stray mark on the bottom of page 75. I don't know what it means. All right. So, yeah, just because I didn't put the XY plane in there, coordinate axes, doesn't mean you can't just chuck it into GeoGebra and do it yourself. It's the kind of thing like I don't think I'm being like slick or anything. It's just that I'm adding an extra step for you to do. All right. That's only if you need to. Personally, I don't think that you always will need to. If you want to put it in just to satisfy the curiosity, you can, but I'm putting it in so that I can satisfy your curiosity. But it's not always going to be necessary because the algebra is going to take care of that. All right. So there you go. I mean, if anything, it confirms that the XY plane is not the axis or the plane of intersection. All right. So we have an intersection that does not occur on the XY plane, which is fine. We still need to know that intersection. So off we go. All right. So I see an x squared plus y squared. So like I said before, I'm immediately thinking, right, that's r squared. X squared plus y squared is equal to r squared. But even better, the square root of x squared plus y squared happens to just be r. So we have z equals r squared. Z equals 2 minus r, z equals r squared. Same strategy as before. Since they're both equal to z, we can set them equal to each other. 2 minus r equals r squared. It's up to you. When you get to a step like this, I'm not at the point where I'm going to get overly nitpicky and dramatic about certain things. Do it in Desmos. It's not an algebra class. Just give me enough to, let's just put it this way. Make it clear that you're not cheating. That's all right? So 2 minus x instead of r. All right. Now, you can just put it in as 2 minus x. For whatever reason, I don't know why, but Desmos accepts this. That's fine. It's graphing the function 2 minus x and graphing the function x squared. Right. I mean, in theory, you should probably put it in as y equals. Right. Left side in is one equation, right side in as another. Find the intersection. In terms of, in this case, I'm using x. So in terms of x, and so we'd have r equals negative 2 and 1. All right, and you could just do a quick double check. If you plug in a negative 2 for r here, you get a 4. If you plug it in for r here, you get a 4. If you plug in a 1 for r here, you get a 1. If you plug a 1 for r here, you get a 1. So you're good. There's no need for you to show me how the great skills in being able to solve a quadratic. All right. And honestly, the only thing showing that algebra can do is hurt you. Because if you screw it up and you opted to do it by hand, then you just put yourself in a position where you're losing credit for something that did not require, you weren't required to do. All right. So back to this. We now know the intersection. Or the intersections. Now, the intersection in Desmos is one thing. The intersection, as it applies to polar coordinates, is something different. All right. So what we have are two circles. R equals negative 2 and R equals 1. All right. So I'm looking at this and saying, all right, well, which one is it? All right. So that's kind of an issue. And then once we get out of that predicament, like, okay, well, how do I manufacture the bounds from this? Well, if I look at r equals 2, r equals negative 2, separately from r equals 1, all right, they're circle equations. All right, this one translates to x squared plus y squared is equal to 4. And this one translates to x squared plus y squared is equal to 1. All right. We're not going to have any domain issues when it comes to the x and y values, because no matter what you put in for x and y in the original function, you're going to get something positive because the sum of squares are positive always. So we're not worried about anything being undefined. But what I'm going to do is I'm just going to pop in the cylinder, just like I did in the last problem, x squared plus y squared equals, we'll start with a 1. And so looking at that, I see that I have a cylinder corresponding with what appears to be the intersection between the two graphs. Right, so that cylinder is the intersection between, or represents the intersection between those two graphs, which is great. If I do a top-down view, it seems to jive, which is good. All right, so now what I have to do is figure out what on earth that whole x squared plus y squared equals 4 is all about. Well, common sense tells us it's just going to be a circle that's wider, right? So if you're looking at where the cone intersects the xy plane, looks like it could be around 2 units. So and there you go. All right. So now I'm kind of looking at it, and let's turn that one off. I'm looking at this and saying, okay, which, if either of them, do we actually need? All right. So I want the area, and I'll go to this diagram because it's a little cleaner now. I want the area that's bounded between these two graphs. All right. So let me just trace that out a little bit. I'll use yellow. All right. So if I go from 0 to 1 for R, right? So here's R equals 0. And over here would be R equals 1. If I do that, it's going to give me everything underneath. Now I'm trying to do a 2-dimensional graph, or, you know, diagram on top of a 3-dimensional graph. So it's not going to be great, but hopefully you'll get the idea. Pretend it looks awesome. All right. So you're going to get everything under that cone over that interval. All right. So that seems to make sense. So it doesn't seem like I want anything beyond 1. So R equals 1. So if I only focus on the cone, that's going to give me more than I need. What I need to do is shave off this stuff here. All right. And that seems to be the volume contained underneath the paraboloid, really over the same interval. All right. So if we can trim off that volume that's trapped underneath that paraboloid over the interval also of 0 to 1, then it looks like we'll have it. All right. So that's what we're going to do. It seems as though we can disregard this. We're going to use this one. This is important. All right, so we need that one. Going from 0 to 1, I'm going to take the double integral. And we're going all the way around with this baby. You know, you can take a look. I'm looking at 3 circles when I do a top view. All right, so if I organize it, you know, it's kind of hard to see, but if I organize it so at least it looks like I'm looking down at the XY plane, I'm not seeing any gaps in this. It's not like we're just stuck in the first octant or anything like that. So we're going all the way around. So 0 to 2 pi. Oh boy, I got to bring it in. My handwriting, as you know. From 0 to 1. Now I'm going to put in my z function. The appropriate z function to start off with is going to be the downward facing one. All right, so that's the cone. All right, now if you have trouble identifying that, then you can just kind of toggle on and off these bad boys. But I will tell you that if you kind of use the profile view, whether it's parabolic or linear, use that profile view as a kind of a way, as sort of a guide. You can probably, in a pretty easy way, pick out the appropriate function, right? Because based on the profile view, the upward facing function looks like a parabola. That's the z equals r squared. Based on that same profile view, the one that looks more linear is the cone, right? Because really what's happening is you're taking a single line and spinning it around the z-axis. That's where you get your cone from, all right? It's made of just a single line getting spun around an axis. All right. So yeah, this is working out nicely, right? Yeah, you can't even when I do it, man, it doesn't matter what angle I change it. It looks terrible no matter how you slice it. All right. But that's really what's happening. All right. He said as if he made any kind of sense whatsoever. So 2 minus r dr d theta. That'll give you everything between the cone, the surface of the cone and the xy plane, and then minus same bounds. Won't always be the case that the bounds are the same. It's nice when they are, though. R squared r dr d theta. All right, and so that'll subtract off all the schmutz beneath the paraboloid between the xy, between the paraboloid, the bottom of it, and the xy plane. All right, and so what we would have here is the expression that we would use to figure out the volume contained between those two surfaces. Right, and it's kind of interesting if you really think about it. You go back to volumes of revolution in Calc 2. You know, when you took a graph and you spun it around the x-axis, you spun it around the y-axis. All that stuff you could have done with the double integral, except you didn't know what a double integral was at that point, most likely. All right, so I kind of look at it as like, I sort of wish they held off on that topic, because in a lot of ways, what we're learning about now kind of makes what we were doing in Calc 2 sort of amateurish, you know? Like why spend the time doing that when you can use this technique, right? And time could be better spent learning some more fundamental skills related to integration, and, you know, maybe even get started on polars and vectors and things like that. I don't know, but that's just me soapboxing again. Anyway, so that was page 75. Nothing too crazy. So let me stop that recording. I'll start a new one.